Hello everyone, in this lecture we're going to discuss Avr interrupts in assembly. So what are interrupts and why are they used for? So imagine you have a microcontroller connected to a switch. So whenever the switch goes low, we need to, let's say, light the LED. Okay, so the way to do it is, or the way that we know how to do it till now, is using a technique called polling, which means busy wait. So the code is stuck in a loop waiting for the input to go low. So what I do is I need to test for this bit. So I use something like SBIC. Let's say this is port or pin D, 2, and let's say I'm gonna go R jump loop, and this is loop. So what happens with the code is that I'm always stuck here until pin D goes low. So this is what's called busy wait. I cannot do anything else. I cannot, let's say, display some message on an LCD. I'm always stuck until the push button is pressed down or the switch is pressed down. What if the user didn't press the push button down? So here I have a problem. So polling works in some cases, but in most realistic cases where we want the microcontroller to do many things at the same time, we have the interrupts. So what are interrupts? Interrupts are a hardware elements that monitors specific components inside the microcontroller. So this is the microcontroller. Okay. So interrupts monitor specific components inside the microcontroller and indicates if an action has occurred via hardware. So this is done in software. Okay, this is done in hardware. So the interrupt monitor specific components. What are these specific components? We're gonna take 3 of them. Timer 1 and external interrupts, PD2 and PD3, which relates to interrupt 0 and interrupt 1. So this is, let's say this is PD2, port D pin 2. So at this pin there is a hardware interrupt monitoring if I set it up correctly. It will monitor whenever it goes low or high or whatever. We're gonna see all the configuration, and when this happens the program execution stops and it tells me that there is an interrupt. And in this way I can do multiple things at the same time. So I imagine I have a code like this. So I will be executing those lines, and then here an interrupt occurs. So it takes me to a special place called ISR, or interrupt service routine, where I perform the desired task, and in my case it's just lighting on this LED. So I will be executing this first instruction, second, third, fourth, and I have many instructions. So wouldn't it be nice if, as I'm executing these instructions, somebody comes and tells me, alright, PD2 went down, so you need to light the LED. So it stops, it goes there, finish executing the ISR similar to a function call, and then returns. So the steps are actually easy when an interrupt occurs. So when an interrupt occurs, first I will be doing something in the microcontroller. I finish executing the current instruction. Then to save the address of the next instruction so that I can know where to go back, because remember, I have many instructions. These are instructions. Instruction happened here, interrupt happened here. I go to the ISR, interrupt service routine, and then I have to return all the way back to the instruction under it. So I need to know this instruction. Of course, I save it on the stack. On the stack. Third, program or PC program counter jumps to a fixed location in memory. I mean by program memory or ROM. Okay, called interrupt vector table. Remember, I have multiple sources of interrupt. I have sources from ADC, different timers, different serial components. So I don't just have a single interrupt, so I can ISR be known directly. So this interrupt vector table has the locations of all interrupts that may occur. So, okay, this vector table, points the microcontroller to the address of the interrupt. We're going to take an example on this. So let's say if timer 1 interrupt, it takes to a timer 1 handle. If an INT0 interrupt happens, or on PD2 on the pin, then it automatically directs it to that specific interrupt, and this is called ISR, interrupt service routine. So fourth, the microcontroller executes the ISR, which is in our previous case just lighting the LED, until it reaches the return instruction. But here we have a different return. We don't have the normal return of a call. We have something called return I, which means return from interrupt. Okay, because this is an interrupt service, it's not a normal function, and this means it keep the global interrupt enabled. We're gonna discuss this later, what we mean by keep the global interrupt enabled. And when return from interrupt is executed, we pop the return address as in a normal call instruction. So these are the steps that occurs when an interrupt happens. So let's take an example of a interrupt vector table. We're gonna take just those three vector table. Of course, this is all for the Atmega 328. So, of course, this is the interrupt, and this is the ROM location. So, whenever we want one of the interrupts that we came across and we don't know that they are actual interrupts is the reset. So whenever we press the reset button, it should automatically reset everything and go to location 000. So reset is one of the interrupts, and the ROM location for this is 0x0000. Now we have timer 1, for example, and in this case timer 1 interrupt is located at location 0x001A. We have also some external interrupt. Location 0x0002. This is external interrupt 0. We have another external interrupt. One, and it goes to the location 004. So this is related to INT0. This is related to INT1. This is occurs on PD2, which is port D pin 2. External interrupt, I mean by it switches and push buttons. This is what I mean by external interrupt. Timer 1 is we noticed that last lecture we used polling to check if 2OV1 is set. In this case, the interrupt will let me know. And INT1 is PD3. Of course, this is port D pin 3. So these are some of the addresses that we need to know. So usually the way we organize our code when we have interrupts is that we don't want to write code overlapping the ROM, the places where we have those reset vectors. For example, so this is the program memory. So here at location 0, okay, we want to have something like jump to main. The way I do it is using the .org directive. I say jump main. So this is remember, this is the reset vector. So I press reset, I always go back to main. So then I need to leave some space for those reset vectors to fill. So I can say, okay, .org 0x100, and this is my main program. Okay, so somewhere here 100 I have main, and this is where my code goes. So notice how I left enough spaces for all the vectors so that I cannot overlap. So now, how can we set up the interrupt, and how can we do this? So setting up the interrupt is very easy. It entitles 3 things. So to set interrupt, I need the global interrupt equal 1. This is the main switch that enables all interrupts, and disables all interrupts. So this is enables all interrupts or disables them. Of course, when it's 0, it's 0. It disables them. So this bit is found in sreg. So sreg bit 7, this is called I. So I is the global interrupt. Enable. And I have 2 instructions to work with it. I have SEI, just like this, which means set global interrupt, and CLI, which means clear interrupt. So remember here that these don't take any parameters. Automatically they know that it's dealing with STRAG bit 7. I could have done something like this, bit set F. I could have set those bits using the normal bit operation in the AVR microcontroller, but in this case I can use something like SBI, which means SBI set bit and the IO. So this is similar, is equivalent to this, and CBI STRAG, 7 is similar to CLI. So as we said, the first step is we need to enable the global interrupt. Since I have many interrupts, I have many interrupts. Okay, I have timer 0, timer 1, timer 0, ADC, all of those, and 0 and 1. These are the 3 interrupts we're gonna use. Each one has a local enabler. So this has timer 1 IE, okay, and this has INT0 IE, and this has INT1 IE. So this is the local interrupt enable. So if you want an interrupt on timer 1, I need to have the bit 7 of SRAG to be 1 and timer 1 IE to be 1. Okay, I cannot just have one of them. So timer 1, it's not called timer 1, T0 IE. Sorry, T0 I1E, my bad. So this is called T0 I1E. Okay, so this is the name of the bit. So to have them both, then to have the interrupt on timer 1, I need T0 I1E and SRAG to be 1. And the third thing is, when the interrupt occurs, there's a flag that tells me the interrupt has occurred. So the flag indicating the interrupt is or has occurred will be set by hardware. So in the case of timer 1, it's TOV1. So TOV1 is set by hardware, and I need to clear it by software. So we know that SRAG is found, the I bit is found in SRAG. What about T0 IE1? So this is found in, so the TOI1E is found in a special function register called timer mask 1, and it's found at bit D0, which is TOI1E. Okay, so this is the bit that I am concerned with. So for timer 1 to have the vector, to have the interrupt. So now for the interrupt for timer 1 to occur, I can visualize it like this. So let's say we have, this is timer 1 or TOV1, this is the flag. So if this is set by hardware, as I said, so the timer expired, the timer hardware sets to TOV1, and then I need to have also TOI1E. So this is the enable that I set it, and then another AND gate with I, so that I can go to vector, jump to vector location, 0x 001A, and the same for INT0 and INT1. So to set up those the T0 I1E, so it's very simple. Setting up interrupts in assembly. So what I do is I say, okay, LDI R20, comma 1 shifted TO I1E. I could have said also LDI R20, comma 0, since this is bit 0, okay? So I don't have R1, sorry, because I want this to be in location 0. And then STS, since I cannot use out in this case. So timer mask 1 R20. So this here I enabled the local interrupt, and then I have SEI, which is enabling global interrupt. Okay, so now that I know how to to enable those interrupts, let's take an example. So imagine I want to create a square wave on port B, pin 5, and at the same time copy port C to port D. So imagine that I have some switches on port C and some LEDs on port D, and I want at the same time to have a square wave on port B. The square wave, of course, I need some timing information. The frequency is 60 megahertz. The period for this, I wanted to have a 4 microsecond period. So period of the square wave, 4 microseconds. This means this will be 2 microseconds and this will be 2 microseconds. I need to divide them by both. So I need my timer to count for 2 microseconds. So if F oscillator is 16 megahertz, this means the oscillator will be 1 over 16 megahertz, which is equal 0.0625. Then I say, okay, so I have 65536 minus n times 0.0625. Of course, megahertz means microseconds, is equal to microsecond, implies n is equal 32, or I can say in hexa 0xFFFE. E0. FFE0. Okay, so this is what's going into timer counter 1 low and timer counter 1 high. So I need a square wave. I did the calculation for the square wave. I need the timer 1 to generate this. At the same time, I want port C and port D being copied as the square wave is generating. So first, it's a typical way of starting a program with interrupts is say origin 0, jump to main. Then of course I have dot origin 0x 1A. Remember, this is the one for timer 1. Then I go jump. I can call it whatever I want. I can call it, so let's call it timer 1 ISR. So this is the ISR. It's not necessary to call it this specifically, but it's a good name. It's an indicative name. So then dot origin. So at 100 I go to the main. So first thing I need to, since I'm using the stack, I need to set up the stack. So I'll get and then I do, and then LDIR20 low RAM end. Remember this will give me the last address in the RAM, and out SPL R20. So first, so step number 1, stack. Step number 2 is that I need to set up my IOs. So first I need to say SBI. I need to set port B pin 5 as input, as output. So SBI DDRB, 5, and then we have LDI 0x R20 0x FF out DDR. So we want D to be output, and LDI R20 0x00 out DDRC, 20. So step number 2, work with the IOs. So here I said, okay, PB5 is input, port D, PB5 is output, sorry, port D is output, and port C is input. So this is just the case for the stack and the IO. I haven't started yet with the interrupts. So now the next step is setting the interrupts. I have 2 things to set. I have to set the local interrupt. So I can say, okay, load R21, and then I have STS timer mask 1, R20. Okay, so in this case I enable the local interrupt and SEI, and enable the global interrupt. So this part is number 3, which is enable global and local interrupt. Okay, so this is the 3rd step. Now what I want to do, I need to set up my timer. So first, since I have a timer, if I don't have a timer I don't have to write this bit. So first LDI R20, I'm using the same register since the values are not important when they are inside the SFRs. Timer counter 1 low R20 LDI R20 0xFF out timer counter 1 high. Okay, R20. So these are the 2. I loaded my timer with the value that he needs to count. Then I say, okay, LDI R20 0x00 and out TCCR1A, R20 LDI R20. This is normal mode, no prescaler, and here I start the code, I start the timer, TCCR1B. This is last lecture if you don't know what I'm talking about right now. So this is the 4th step. The 4th step here is timer operations. So this is all from the previous chapter. This is how you configure the timer and you start it. So now what I want to do is this is the main program. So I say here in R20, pin C, and out port D, R20, and jump here. So after I start with origin 0, I go to main, I go ahead, continue, I set up the stack, I set up the ports, the IO, set up the interrupt, and then the timer. And this is my main program where I want port C to be on port D. Okay, so now I need still to write the code for the interrupt service routine. So what happens is that I need to write, so let's say I'm going to place it in .origin. This is just directly under this part. I'm going to write it in red. So this is timer 1 ISR. So first thing is I want to set I need to read the value of port B. So I'm gonna do R15, port B. Of course, I'm only interested in bit 5, so I'm gonna do a mask. So what this is, I'm loading with 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is used for toggling, and then I do exclusive OR so that I can do bit flipping. So this is just flipping the bits, and then out port B, R16, and then of course I need to reinitialize the counter, the timer. Sorry, this is R18. This is R18. One high and R18, and return from interrupt enable. Sorry, return from interrupt. So this part is just for toggling PP5. So what I'm saying here, that if it's 0, okay, then I waited for 2 microseconds, the timer expired, then I XOR it with 1, so 1 and 0 will be 1. So the next time I come, it's 1, it will have waited 2 microseconds, and then 1 and 1 will be 0, and so 2 microseconds. This is how I'm creating the on PB5, okay? And this is just to for timer initialization. Okay, so if I look, so here we have, so as I'm copying port C to port D, the interrupt occurs. So I finish executing this instruction. Automatically, since the microcontroller knows that this is a timer 1 since a timer 1 interrupt, since I set the interrupt for timer 1, it directs it to 1A. What do we have in 1A? I have the address of timer 1 ISR, which is this one. So I continue on drawing the square wave. Okay, so this is what happens. Wherever I am here in the main code, even if it's many instruction big, so I keep on executing. Once the interrupt hits in a certain instruction, it finishes executing this instruction, automatically jump to this address. If I don't have anything here, then the interrupt will not occur, and automatically I go ahead and execute this code. Okay, so this is the interrupt for timer 1. Now, for the second type of interrupts, we said we have two more types, which are or same type but two different variations. We have external interrupts. The external interrupts are on two pins. They are in port D, pin 2 and pin 3. This is INT0 and this is INT1. So this is also this is for port D, both of them. So as with the timer 0, I have a local enabler, and this local enabler is found in EIMSK, okay, which is called external interrupt mask. Now, this register has two bits of interest to me, INT1 and INT0. This is the enablers. So INT0 enables interrupt 0 and INT1 enables interrupt 1. Okay, we have also, as we said, those interrupt pins are usually useful for connecting switches to them. For example, if I have an active low switch, so I can do something like this, and I can have an active low switch whenever it goes down, or I can have also something like a push button, for example. Okay, this is PD2, this is PD3. This is called edge triggered, and this is called level triggered. Because for this I need to close down the switch so it's on a low level here, where in this case I need to have a falling edge. So this is the edge triggered and this is the level triggered. Okay, so I have different flavors. I can have them working with active high, active low, or on change. So the main registers that are responsible for this is found in ISFR called EICRA, which is called external interrupt control register. Register A. And in this we have 4 bits of interest to us. We have ISC11, ISC10, ISC01, ISC00. So this is for INT0 and this is for INT1. So in case ISC01 and ISC00, they can take 0, 0, 0, 1, 1, 0 and 1, 1. So in this, if I place 0, 0, which is by default, I go with the low level. So this is on low level INT0. In this case, for 0, 1, this is interrupt on change. So interrupt on change. So whenever it changes, okay, it goes down or goes up, okay, whenever I have a downward or an upward edge, then I have interrupt on change. I can have interrupt on falling edge. This is falling edge INT0, and I have also one for the rising edge INT0. Of course, the same configuration happens for INT1. So whenever I want to use INT1, I use ISC11 and 10, and whenever I want to use INT0, I use ISC01 and ISC00. So if I take some examples on this, I can say, okay, how can we configure INT0 falling edge? Okay, and then I can say 1, 2, INT1 triggered on any change. 3, INT1 rising edge. So first I can say LDI R20, come on, 1, ISC 01. This means a fancy way of saying R20 equals 0x02, and then I can do SBI, or sorry, STS, I cannot use the I's, STS interrupt, external interrupt control register A, R20, alright. So for 2, I can say LDI R20. In this case, I want just triggered on any occasion. So 1 shifted ISC 10. So this means R20 is equal to 1 to 4. Remember, ISC 10 is 4. Okay, so this is 1 is equal to 100. So if I look at ISC 10, so this is 0, 1, 2, so I shift 2. So this is 0, 1, 2, 3. And then I do STS R20. The third one is LDI R20. If I want to do it the fancy way, 1 shift ISC 10, 11, or 1 shifted ISC 10. This means this is 1 and this is 1, or I can say R20 equals 0x0c. So instead of this, I just write 0x0c and it has the same meaning. But just in case you see this notation. So this is how I can configure my interrupt into different places and different edges. Now let's take a problem. So let's say I write a program that configures INT0 pin as interrupt, and when low, and whenever this happens I want PB5 to toggle. Okay, so in this case I start the same way, jump main. Now the address for the interrupt vector for INT0 is 02 and INT1 is 04, so we're gonna use 02, and then I say jump, I say INT0 ISR. Okay, so in the main, remember here I don't have any timers, so I don't have to do anything for the timers. Of course I go ahead now, step 1, initialize the stack. And of course low RAM end. Now I need to set the output DRB. So this is step 1. Now I'm step 2. I just have, and I need to have PD2. So INT0 means PD2. So CBI DDRD, comma 2. Now, so in this case, I also need to set up for low level. Since it's a switch, I'm going to use the low level. So I need to place 0, 0 on the external interrupt control register. So LDI 0x00, and then I go STS. It says R20. R20. Okay, so here I said I want on the low level, and of course I need to set up INT0. So I go ahead and say, okay, I'm going to continue here. LDI R20 1 shifted INT0, and then I say out A1 mask R20, and here I go with SEI. You need to notice which registers we use out with and which registers are used with STS, the same as E1, the interrupt, external interrupt control register. Okay, and here I can do, this is my main program. So jump here, jump here. Here I can do whatever I want. So that assume that here I have a very big problem. And now, what's the interrupt routine? Interrupt service routine. It's very easy. This is INT0 ISR. So of course I need to toggle port B. I'm gonna do it the same way as I did in the timer. So I'm gonna read port B. I'm gonna use a mask for this, XOR R21 with R22, and then output this value on port B, and then I have return from interrupt enabled. So in this case, this is just toggling. Whenever I push the switch, or I close the switch, port B will toggle. So I will be somewhere here doing nothing. Interrupts occur. It goes to this address. It knows that it's INT0 because I closed the PD2 and it went low. So once it went low, it knows that the three conditions occurred. The device went low. I have INT0 is enabled. I have SEI enabled. This means I can go to the interrupt table, vector table, and jump into INT0 ISR, and in this case I toggle port B. So as you see, the interrupts are a very nice way of taking input from the user or waiting for timed event without stalling the microcontroller or stopping it from doing its job.